This video is going to be on section 3 of chapter 7, which is basically about using and proving triangles are similar. So we're going to go through how to prove two triangles are similar using the AA theorem, which we talked about in the last video a little bit, and then we're going to go through some other similarity stuff here in this rather shortish kind of video. So we're going to go through some setups that are maybe unique compared to the last one. So in the last video, we had two triangles that were separate, and we said, okay, this triangle is similar to that triangle. Find these missing pieces. So again, we had something like this, where we had this triangle over here, we had this triangle over here, and we said that they're similar, and we said, okay, if this piece is x, and this piece is 5, and this piece is 10, and this piece is 6, find out what x is. So we set up a proportion, we cross-multiplied our numbers, and then we got what x was. So now we're going to be taking a look at a few situations that are a little bit more advanced than just two separate triangles. So this would be one of them. So it says find Q and P given this setup. They don't tell you which triangles are similar, and they don't give you much more information to go off of. So what you have to notice here is that this is a very common setup where you have a triangle inside another triangle. So we actually have two triangles here. We have this triangle on top, which is our small triangle, and then we have the big overall triangle that it's inside. So we're looking at those two triangles, and those two triangles are the triangles that are similar. Now, how do I know that those two triangles are similar? Well, because they have two congruent angles. So they both share this angle right here, angle M. So angle M is obviously congruent to itself. And because that these lines down here are parallel, that means that these two angles are congruent and these two angles are congruent. And the reason I know that is because they're corresponding. If you were to match this out into that little setup that we usually have, we'd have that, again, this angle right here is in the top left, this angle right here is in the top left of its set of 4, therefore they're both corresponding. And we'll talk a little bit more about that when we get to proving triangles congruent. But this is a very common setup, and again, it's just always the same case too. The top triangle is similar to the overall big triangle, not congruent, but similar. So now that I have this marked down, I can start making my proportions here, because again, I need to get two fractions to get equal to each other here. So be very careful how you set this up too. Let's take this side right here, QM. QM. Well, QM is 5 units long, so we'll put a 5 up here. Now QM is matched up with the single arc and the double arc angle. So what would that match up with in the big triangle? Well, if I match the single and double arc in the big triangle, that would be single arc up here, double arc way down here. So that would match up with this entire side here. So most people would just say 5 over x. But this entire side length is not 5 over x. This is actually 5 plus x. So it'd be 5 over 5 plus x, because that's what this entire side length is right here, is 5 plus x. I got a little carried away there in my tracing. So when you have a triangle inside another triangle, you often have to add pieces together to get the big triangle. And we can do the same thing on the other side. So this 6 right here is between the single and the triple. That would match up with this line right here, MO, which would be 6 plus 3 3/5. Because that entire length is both sides together, not just one. So first off, what I would do is I would keep my first fraction the same. I figure out what this is, so this is going to be 9 3/5. So 9 3/5. And then we're going to cross multiply. Now remember, when you cross multiply diagonally, you're taking this 6 here and multiplying to both parts of the bottom number. So 6 times 5 is 30, and 6 times x is 6x. So again, you don't just take the 6 times the 5, you take 6 times everything in the bottom, because you're basically distributing the 6 down there. And then you would take 5 times 9 3/5, which I can probably do in my head, but I don't want to right now. So we'll take 5 times 9 3/5. So 9 3/5 literally means 9 plus 3/5, so I'm going to type it in this way. And we get 48, right? And then we solve this like an algebra problem now. Subtract, subtract. We get 6x is equal to 18. And then divide by 6, and we get x is equal to 3. Now it says find QP and MP. So QP is 3, because that's just what x is, which means that MP is going to be equal to 5 plus 3, which is 8. So QP would be 3, because that's just x. Q to P is x. M to P is going to be 5 plus x, or 5 plus 3, which is 8. So the key thing here is that when you have a triangle inside another triangle, whether it's on top, on the side, or on the other side, so another version of this would be this type of picture. So you have the smaller triangle over here, and then you have the big overall triangle as well. So this doesn't necessarily have to be a top and bottom thing. This can be a side thing as well. But the idea is that when you're setting up your fractions, it's small piece over big piece, which is the entire length. So don't forget to add these two sections together to get the big piece when you're setting up your fraction. Otherwise, again, you're going to be off by some numbers. Whoops. So other times we'll often have to draw our own diagram. So that might just give us a description and we have to draw it ourselves. So Adam is standing next to a building. Adam is 6 feet tall, so let's draw a ground here. Adam is 6 feet tall and the length of his shadow is 9 feet. Let's draw that real quick. So Adam's right here. He is 6 feet tall and his shadow is 9 feet. So 9 feet. And it says he's standing next to a building. And it says the building's shadow of the building is 322.5 feet. So I'm going to draw it this way, even though technically speaking, if it's a shadow, it'd probably be going in the same direction. But just for clarity's sake, we're going to draw the shadow of the building here. And that's 322.5 feet. We want to know how tall is the building, x. Well, one thing you need to know about stuff that's been standing or built on the ground is that otherwise, unless otherwise stated, you can always assume that stuff that's built or standing on the ground is standing at a right angle. So this is a right angle here with the ground, or what would be the ground, because I had to draw the shadow a little bit up. And then there's a right angle here with the person and his shadow or the ground. So these are actually two similar triangles. Boom, boom. Whenever you're dealing with shadows, whenever you're dealing with shadows, you can always assume that they're going to make a similar triangle with other stuff dealing with the same shadows. So the reason for that is basically because if you have a sun, which we do, the sun's rays run parallel. So when I have a person here, the angle of their shadow is going to be the same as if I have a building here and the angle of it is shadow. So the length will be different, but the angle of the shadow and the angle of the ray is going to be the same. So therefore you have congruent angles and therefore you have congruent triangles, which is a brief description about why this works. But in terms of the overall concept, just remember that anything dealing with shadows usually deals with similarity, both whether it's from the sun or a flashlight or whatever. Shadows usually are similar objects. So because these are similar triangles, we can start piecing them together. Now, we don't really have a label to go off of, but we do have ideas, essentially, or concepts. So for example, instead of doing, like bottom to bottom, think about it as person height, PH, building height, BH, and then person shadow, PS, building shadow, BS. So you can think about it in terms of their concepts rather than their positions on the diagram that you drew there, if that's helpful for you. Height over height, shadow over shadow. As long as you're consistent with how you set up your fractions, you'll be okay. So the person's height is 6 feet. The building's height is x, because I don't know it. The person's shadow is 9 feet. Again, person on top, building on bottom, building on bottom. As long as you commit to one way, you have to commit to the entire problem like that. And the building shadow is 322.5 feet. And then now we just cross multiply like we've done before. So this would be 9x is equal to, let's do 322.5 times 6 gets us 1935. And then we divide by 9, and we get x is equal to, divide by 9, 215. And that's how tall the building is, 215 feet. So if you have a word problem, again, the idea is you have to draw your own diagram. Now, do you necessarily have to draw it if you can do it in your head? Maybe not, unless your teacher requires you to. But it's always helpful to do it anyway, just because it's really easy to miss up numbers and kind of mix numbers around if you don't have a diagram to go off of. Like, it would be very easy to switch up, say, this 9 and this 6. If you don't have a diagram to kind of help guide you there. So I always recommend drawing out a quick diagram just to make sure you're keeping everything on track here. So it says identify the similar triangles and find the measures. Let's go ahead and do that real quick. These are more typical. The first one's more typical like we had in the last video. So we have two separate triangles. It asks us to find out what y is, essentially, find out what xz is. So we have to figure out, okay, how are we going to set up my fractions here? Now, they don't give me any labels, so I'm going to use the angles to help guide me on how I'm setting stuff up. So 5 here is between the 49 and the single arc. So I'm going to figure out what piece on the second triangle is also between the 49 and the single arc. Well, here's the 49. Here's the single arc. So that'd be 4. So 5 to 4 would be my first fraction there. So single arc 49, 5. Single arc 49, 4. Then my next one, y, is between the single arc and the non-arc. So what number here is between the single arc and the non-arc? Well, that would be 5. And then now we cross multiply just like we did in the last video. We get 4y is equal to 25. Divide by 4, and we get y, there we go, is equal to 25 fourths, which is some decimal that escapes me at the moment, 6.25. And that's our answer. So this, again, this is like the last video problem. This is like what we did earlier in this video here. So the second one here, when it says find VS, which is the entire length here, which they call X. This, again, you have to be careful that you're actually taking full lengths to full lengths. So first off, let's get my fraction set up. Again, I have the small triangle here, RTS, small triangle, and the big triangle, QVS. And they're similar, because one's inside the other. So if I look at 3 here, 3 goes up and down, and it's attached to the right angle. What piece corresponds with that in the big triangle? Well, 5. 5 goes up and down, and it's also attached to the right angle. So 3 would match up with 5, because they both go the same style. Right angle up and down, right angle up and down. So they're going to match with each other. Now the question is, what about my other ones here? And this is where you have to be careful. So 12 goes from T to S, which would be undoubtedly the part of the small triangle. 12 goes from T to S, and it's on the bottom of the right angle mark. So that means that the bottom of the right angle mark in the big triangle is V to S, which I'm going to put down as X, because it tells me that that distance is X. So some of you might be saying, well, isn't this X plus 12? Well, no, because this X, it says right here, this X goes from V to S. It's that entire length. So I don't need to do X plus 12 here because it's already covering the entire length anyway. If they just said, if this was gone, and they just said that VT was X, then you'd be right. Then I'd have to do X plus 12 on bottom because X just covers from V to T rather than from V to S. But because they put down that thing on the bottom, and because they said that the entire length is X, I can just use X in this case. So again, be very careful on your diagrams. Make sure you take the time to read them so you don't make silly mistakes. So cross multiply, we get 60 is equal to 60 is equal to 3x. Divide by 3, and we get 20 is equal to x. Okay? So that's as simple as it gets there. Again, when you have a triangle inside another triangle, just take your time and look and make sure that you're piecing the right pieces together by checking to see, do they match up in the same direction? Are they actually corresponding? Do these represent the same pieces? That sort of thing. Use the angles to help you out. Keep doing that. Come on. There we go. So this is another one way to draw the diagram here. So it says a cell phone tower cast a 100-foot shadow. So I'm going to draw that right away. So a cell phone tower, let me draw it differently. Cell phone tower cast a 100-foot shadow. So there's the shadow, poorly drawn, 100 foot. At the same time, a 4-foot 6-inch post near the tower cast a 3-foot 4-inch shadow. So here's a post that's 4 feet 6 inches, cast a 3 feet 4-inch shadow. Find the height of the tower. So the height of the tower is x. Now, we know that these are similar triangles because they're dealing with shadows here. The issue here is that this is just pure 100 feet, and this is 4 feet 6 inches, and this is 3 feet 4 inches. So it'd probably be helpful if we convert either both of these into just pure feet, or convert both of them, oh sorry, not both of them, but all of them into inches. Let's go ahead and convert both of these into pure feet. So 4 feet 6 inch, let's go ahead and convert that into just pure feet. So 6 inches means 6/12 of a foot, which is 0.5. So this would be 4.5 feet. And 3 and 4 inches. So 4 out of 12 is 0.3 repeating. So this would be 3.3 repeating feet. So just a little bit of a conversion there to make sure that everything's in the same units before we start matching them up here. So we're going to take shadow to shadow and height to height. So I'm going to do post to tower. So post height is 4.5. Tower height is x, because I don't know it. Post shadow is 3.3 repeating. Tower shadow is 100. So now I'm going to cross multiply here. 3.3 repeating x is equal to 450. Divide by 3.3 repeating as best I can. And we're going to get 450 divided by, the way you do it in the calculator, if you want to do it the lazy way, is just 3 point and then just type in a bunch of threes. Boom, 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 boom. And then you just click enter and you get 135. So the tower is going to be 135 feet tall. Now, you can do a common sense check here. Does this make sense? Well, my fractions do agree. So this is height to height, shadow to shadow, and it's post to tower, post to tower. So they're all consistent in how I made them. And it says here that the post is taller than the shadow is long, right? The post is 4 feet 6. The shadow is only 3 feet 4. Now, if I do this correctly, my tower should also follow that. So my tower should be higher than my shadow. And it is. 135-foot tower, only a 100-foot shadow. So because that is also preserved, because that relation is also preserved that the object is more than the shadow, that means that I probably at least did something right. It's a good kind of common sense quick check there. So how to prove this? So proving triangles are similar usually requires use of the AA theorem. Now there are other theorems that we'll get into later, but the AA theorem for proving triangles are similar is probably the go-to one, which basically means that if you can prove that the triangles have two pairs of congruent angles that are corresponding, then you can say that they're similar. So all you need is two angles, not three sides, not two angles on a side, just two congruent pairs of angles between the triangles, and then you can say that they're similar by the AA theorem. Now, luckily, we have a few ways we can get congruent angles. We have vertical angles that are congruent. We have corresponding angles and interior alternate angles or alternate interior angles that are congruent if you have parallel lines. We have either supplementary or complementary pairs that we can maybe get some congruencies off of. So proving angles congruent are actually one of the easier things. If we had to prove that two sides were congruent, we'd be a lot more limited. Bisectors is another one that can help us prove angles are congruent. So we have a few options here. So let's look at two quick proofs here. So it says, given that Li is parallel to Kj, prove that HLI is similar to HKJ. Okay, so I know that they're parallel. Let me go ahead and write my two columns here. So given, and put this down here. It's a given. So I know that they're parallel. So if I hear this word parallel, if I see the symbol for parallel, that means I'm automatically thinking of corresponding angles and alternate interior angles, because those are two angles that pop up when I have parallel stuff going on. Well, one of the things that often happens that people miss is that when you have this set up and these two lines are parallel, angle HLI here, this angle right here, is corresponding to HKJ here, this angle right here. These are corresponding angles, and therefore they're congruent. Angle HLI is congruent to angle HKJ. Now, why are they congruent? Well, because they're corresponding. So if you block out this right half of the triangle set here, if you think about this as, a set of four angles, so 1, 2, 3, 4, and this bottom one as a set of four angles, 1, 2, 3, 4, just extend the lines a little bit. These are both in the same position, top right angle, top right angle. And the baseline are parallel between them. So if the baselines are parallel and the angles are in the same position of their sets of four, that means they're corresponding, and that means that they're congruent. And the same holds true for these two angles right here. So HIL and HJK are also congruent. So HIL is congruent to HJK because both are corresponding sets of angles, so corresponding angles. Okay? So always be on the lookout for that when you have a triangle within a triangle situation, because those are two free angles, and then now you're essentially done. You can say that triangle HIL is similar, not congruent, but similar to triangle HHKJ because of the AA theorem, because AA. So when you have a parallel as a given statement, you're given that these two things are parallel, then you're automatically thinking of, okay, corresponding angles and alternate interior angles. So again, alternate interior angles are the ones that form that Z shape. So if I have two lines here and I have a line here, alternate interior angles would be like if I outlined a Z. So there, there, there. These two angles here would be alternate interior. And then you can do the same thing from the other side and go this way, up and over. But look for the Z shape for alternate interior angles. Corresponding angles, you just have to kind of get used to looking at the picture. So that's why I kind of extended the lines here to make them groups of 4. And then once I have them down to groups of 4, I can see if they match up with the corresponding positions. In this case, they're both the top right of their sets of 4. Now, sometimes they might say prove that these two sides form a proportion. So prove that AE over ED is the same as BE over CE. And again, it says given that these two lines are parallel. So that would be this line right here and this line right here. Given those are parallel, prove that these are the same here. So this is no different than saying prove that this angle is congruent to that angle. When we dealt with congruent triangles, we had that thing CPCTC. That said that once you prove triangles are congruent, you can match up any two corresponding sections and say that they're congruent by CPCTC. Well, because we're dealing with similar triangles, we don't have CPCTC, but we do have corresponding parts of similar triangles are proportional, CPSTP. So corresponding parts of similar triangles are proportional. And proportional, remember, just means that they make a fraction. This literally means that these two things are proportional. A fraction is equal to a fraction. So all I'm going to do is prove that triangle 1 here is similar to triangle 2, and then I can say that this is true by CPSTP. So start with my given, given, given. Come on. And then that goes here. Now again, they're parallel, so I'm automatically looking for alternate interior angles and corresponding angles. Now I can actually, this one's a little bit easier to do alternate interior because I have the Z pattern kind of laid out for me. If I outline this here, I have a Z pattern going from this one. If I start here, I go up the parallel line, then up the transversal, then up the last parallel line. So that gives me this sort of elongated Z shape here, which means that this corner angle right here, this corner angle, angle D, is going to be congruent to angle A here because they're both the corners of this little green Z going through here. Okay? So the corner angles are going to be congruent because of alternate interiors. So I'm going to say that angle A is congruent to angle D because of alternate interior angles. Okay? Now, another thing I'm going to do, I could use the other Z pattern too, so I could go the other way and prove that B and C are congruent because of alternate interior angles. But just to make sure you don't forget, always be on the lookout for things like vertical angles, because vertical angles should be a free congruency pair, right? So something like, there you go, something like AEB here, this angle, and CED here, this angle, those would be automatically congruent because they're vertical. They form that X shape. So remember, if you have an X shape, top and bottom are congruent, left and right are congruent because of vertical angle theorem. So I would use that automatically too. I probably should have used that first even because, like I said, those are essentially free congruencies you can use here. And that's by vertical angles. And if I want to, I could say B and C were congruent also because of alternate interior angles because those would make the Z just in the other direction. But I have all I need here. So I can say that triangle AEB is similar to triangle. So I said AEB, that'd be similar to triangle DEC by AA. And then I can say my proof statement that these sides make a proportion. So these sides are proportional to these sides. And why are they proportional? Well, because I've already proved that the triangles are similar. So CPSTP. Once I prove the triangles are similar, I can say the sides are proportional essentially because the triangles are similar. So think of this as saying, well, because the triangles are similar, I know their sides form proportion. That's essentially what that CPSTP says, just in an acronym. So it stands for something too, but if that's easier to think about, then go with that. And I believe that's it for this video, right? So again, just this video was about a new style of algebra similarity problems like this here, where you have to draw your own diagram, or like this here where you have a triangle inside a triangle, so a new little algebra issue we had, and then about how to prove triangles are similar. So you have this case here where you're proving the triangles are similar using corresponding angles and vertical angles. You could also say that angle H is congruent to itself because of reflexive, because if you notice here, both of them contain an H. So you'd say that angle H is congruent to angle H because of reflexive, and that could give you your second angle too. Or you're proving that two sides form proportion, two side pairs form proportion. In this case, you follow it just like you would a normal theorem. Prove the triangles are similar first, and then finish it off with CP/STP. So if you have any questions, again, let me know. Don't be afraid to contact me. Otherwise, hopefully this video helped you out. Have a good day, night, or evening.